record the whole thing, but let's start here. So density is mass over the volume. This is a ratio. This main formula, I can get out of this main formula 2 more formulas. So I can make 2 more formulas here. I say I can determine the mass, which is density multiplied by the volume. This is another sub-formulas here. Sub-formula. Second one, I can determine the volume. I say the volume is the volume is mass over density. So when it comes to the quiz or midterm or final exam, you have to have the ability to play around the formulas. You don't have just to memorize formula as is, but you will be more flexible to work on the formula itself. Not always the density is asked. Sometimes they will give you the density, the volume. They will ask you to determine the mass or the volumes and so on. So, and you have to watch for this one here. You have to watch the sig fix. So sig fix, significant figures is very important. You have really to address sig fix. So sig fix. Significant figure is very important. Your answer might be correct, but you did not observe all the multiple choices you have in the final exam because you missed one of the choices, which is correct, because you are looking for the correct answer to sig fix. The sig fix has to be applied, and you have to know the rounding, how much that is, and then you have to look at the multiplication, division, subtraction, and addition. So what else about the density we have to know? Well, density is intensive property. What means intensive property? It means it does not depend on the amount. I can measure the density of one gallon of tap water. I can determine the density of 1 drop of tap water. The density of one drop H2O has to equal the 1 gallon density. So it does not really depend on the amount. It's amount independent. So that's the very important thing. It's intensive. Extensive, that means it depends on the amount, such as the mass, correct? Temperature. Those units are really dependent on the amount itself. So what else we have to know about the density? Well, density is always, although it does not depend on the amount, it does depend on, so we have 2 factors here, which is pressure and temperature. If you change the pressure, the density will change. If you change the temperature, the density will change. Correct? So it's intensive, yes. It does not depend on the amount. However, the conditions has to be met. And all the time we take our conditions, V is 1 atm, and most of the time, the lab, we use T is 25 centigrade Celsius. 25 centigrade Celsius. Those are the densities are used for most of the research labs. Even if you're graduating for Ph.D. master degree, that's the very pleasant condition we are in. It's a little bit cooler here than 25. I can feel it's about 22, I think. We have a thermometer, we can tell. I can tell that's not 25, but it's not that big difference in the temperature here. So it's about 22, which is close to 25. But those are the conditions are used in the lab. What else we have to know about density? Well, let's look at this. We look at the density with the units. We have to look at the density with the units. Well, The density units. So we have solids, gram per centimeter cube. Liquids, trying to get this one here. Liquids, gram per ml, correct? And gases, then we have gram per liter. Gram per liter. So anytime I use a solid, I use always gram per centimeter cube because that's very dense. Liquids is moderate in the density of the atom of the particles by themselves, so gram per ml. And the gases, because they are spread all over the places, gram, they have large volume, we use gram per liter. So any question you have about this? I want to go to the procedure because the time is a lot of straightforward. It's not really difficult, but there's a lot of stuff going on with the density. You determine about 1, 2, 3, 4, 5, about 6 densities. But I hope everybody will be able to finish on time. It's a long lab. It's very straightforward lab, but it's long lab. So the first one here, we have to determine the density of liquid unknown A and B. As I said, I saw A, but there might be B somewhere there too. So the liquid looks like this, A and B. So how we do this? Well, it turns out to be straightforward. It takes a dry empty container here. You use a small a beaker, or you can use a beaker, or you can use Erlenmeyer. So from your drawer, pick up a beaker, correct? So how we determine the unknown of this unknown liquid A and liquid B, which turns out to be solid. So I take the small beaker from my drawer, weigh this small beaker empty. Weigh it what? Empty. Everybody's following? Then I take pipette out of this. I pipette out of this 10 ml. I'll show you the pipettes at the back. I pipette out of this 10 ml. Put this 10 ml in the empty small beaker from my drawer. I just got the mass of it from the balance, and then go and reweigh the whole thing. The difference in weight of the beaker empty and the beaker filled with 10 ml will give me the mass of what? Will give me the mass of. Everybody has goggles here. Everybody has goggles. Everybody has goggles here. I want you from next week on, you have to bring your goggles. You have to bring your goggles with you. Those goggles are sitting here for a long time, therefore cannot use them as is. You have to clean them and rinse them with the tissues here because they are collecting a lot of chemical vapors. So you can bring your own, like my own here. Goes about, I think, $2 in Home Depot. So if you go to Home Depot, for example, or Walmart, it's about $2. And then we'll be using them for the second sequence, 1212, and maybe for microbiology or whatever. So in the lab, we have to have last week, and the last 2 weeks, it was not the lab. It was more or less we are working with the computer Excel, correct? So more or less it's measuring. There's no chemicals. But today we'll be running into chemicals, so we have to have goggles. So you can bring yours, or you can use one of here, but you have to wash them first. So this box, but return them. Don't take them home. Those are property of the school. You can buy your own from Home Depot, $2, or from Walmart for $2. Now, I'm not saying anything about the bookstore. The bookstore selling them about $8. So you can buy about what, 4. the price from the bookstore. So I'm saying don't buy from the bookstore, but the bookstore is very expensive. Well, $8, $7, $8. So Home Depot, Walmart's about $2. It's up to you. But I wanted to bring your own. It's much better to bring your own because you will trust your own clean. There's no vapor in your. So this is my backpack. Get it from home. I trust that there is no vapor, chemical vapor or something. I go home and clean it as well. Are you following me here? So it's up to you. If you want to use those, you have to clean them. You have to rinse them with tap water. So this unknown, we weigh the mass of it. Let me repeat. The mass of the unknown is as follows. You take small beaker, weigh it empty. It says here, weigh it first empty. Then you fill it with exactly 10 mL with the pipette. I'll show you the pipette in the back. 10 mL of the unknown. Go and reweigh the whole thing. So now your density is what? Your density is the difference of the mass. Mass is here, beaker empty, filled with 10 minus empty will give you the mass of this 10 mL. Divide the mass over the volume, 10 mL will give you what? Will give you the density. Everybody is following me here? Everybody is following? Straightforward. Take small beaker, empty, weigh it, empty, record the weight, the mass of it, and fill it with exactly 10 mL. I'll show you how to use the pipette in the back. So when you use the 10 mL, go and reweigh the whole thing with filled now. The difference in weight of the mass will give you the mass of this 10 mL. This mass has to be divided by the 10 mL of this unknown A. Here I have unknown A. You might find unknown B over there. I have to check. So this is the first one. Now let's go for the second one. So this is for this is for A and B, but I found only what? I found only A. If you don't find B, just skip B. So if you don't find B, just skip it. But I think you might find it in the back. Now we have to determine. We have to determine two solids of unknowns. We have to determine two solids of unknowns. One is regular, one is irregular. My intuition is telling me this is aluminum. Now, how I can tell if I have aluminum, zinc, or copper, or iron, or lead? Somebody will tell me? Without measuring the density, just by inspection. So, this is my intuition will tell me this is aluminum. Why? Aluminum is lighter. Now, iron with the same size will be a little bit heavier. Now, if I have lead, it's much, much heavier. Lead is much, much heavier. So sometimes it's just by inspection. Lead is darker. Aluminum is more shiny. You see here? Light and very shiny. Lead is very dark. The iron in between. Now, if I have copper will not look the same. Copper is heavier, close to iron, but copper will look golden. Not shiny silvery here, the golden type of color. So sometimes by inspection, you can tell which your unknown is. You don't have to do all this big experiment. So this is regular because this is cylinder, correct? By measuring the length and the area here, multiply the area by the length, give you the volume. So I can determine direct by the measurement. But we'll not do this, we'll do it the other way. This one here, irregular. So we have regular and irregular. So those shafts here, those shafts you can see them. You can see how light they are, very light. That has to be aluminum. Not zinc, not any other else. They are shiny. They are very light. You can feel them. That has to be aluminum is the lightest one from all. Okay, so we have to determine those regular cylinder and of aluminum, and the irregular one, which is the shots one. So how we do this? We'll do this one here through the displacement method. So how we do displacement method? For example, I fill this graduate cylinder. We'll come back and look at in details. I fill this one here, the graduate cylinder, say to whatever number that is, 5, 10, 7, right? So the main thing is the whole object has to be totally covered. So I eyeball the length of this or the height. So I have to add more. So here is, this is 30, 35. I'll add up to 35 tabor up to here. I will record what? Record the initial volume of the tabor, which is, I will add 35, correct? 35 ml. But before immersing this one here, I have to weigh this one empty. I have to do what? I have to weigh this one what? Empty. So I know the mass of this cylinder here, which is minus, you should tell me this is, has to be, right? You'll see 2.70. The copper and iron is 8.9. The lead is about 11, even more denser than the. So here it is. I know the mass of it. I weigh it with the balance. I'll come here, 35 mils. I tilt this one here, 45 degrees. And then I will insert slowly here. So I avoid any splashing of the tabor out. Slowly here. Straighten up the graduate cylinder. You will see that the solid insertion will lead to the tabor level will go up. So I know that initial 35 might be go few milliliters, maybe 40 mils. So 40 minus 35, how much? 5. So I know the mass of this, and it went from 35 to 40. This is final minus initial. That's 40 minus 35, 5. So will be the mass of this minus 5 of the volume of this cylinder. You got that? This is regular. This is cylinder. So you will do the same thing here with the irregular one. Now the irregular one is a little bit trickier when it comes to weighing. So the best thing is to take a weighing boat. Here is telling you take a weighing boat, right? Take about maybe 3 to 5 grams. Here, this is irregular one. About this one will be okay. Maybe more a little bit. Don't take a little bit. If you take a little bit, so you have problem with the air bubbles. So this one here about 3 to 5 grams. So you put them in a weighing boat, but before you do the weighing boat, you have to tear the balance. So the weighing boat reads what? 0. The weighing boat will read what? 0. So you tear the weighing boat mass, then you put this one in the tab, will give you the actual mass of these shots. This is irregular. So then you will do the same thing you did. 35, maybe this time you will add 43, so for example, 43 mils, whatever. Put this one here. That's initial reading. Grand cylinder, what? Initial reading. Tilt it 45 degrees. You put it in. Slowly, 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 slowly. Okay. So here it is. And the tabor will go up. So by few milliliters. So the final reading minus the initial reading of the level of H2O will give you the volume of these shots. Now, whenever you are done, please, I'll put the tissue in the back. Do not dump those in the trash. Do not dump those in the trash. What you will do, you can't all the tabor in the sink and then take them in your hand, put them in one of the tissues I'll put in the back, because we keep them dry to the air and then reuse them. This is the waste to throw them away, correct? So we have to use them. So do not throw them. If you throw them, I'll take some points from your lab reports. So that's a lot of money and it's thrown in the trash. It's not good. So we are using those, recycling them. They are wet, just tabor. It will evaporate. A couple hours, it's already dry. Are you following me here? And then just put them in there. I'll put them in their place here. Here it is. They are wet. Just keep them in the top of the tissue. They will be dried by air. So this is regular and irregular. I use the direct method. So okay, so the density of solid unknowns, we use the displacement method for both. Here you can see that's the same thing here. You tilt 45 degrees. Make sure that the tabor will not splash out of the graduate cylinder. Slowly, the insertion of this unknown solids has to be done by feeling. Don't just stop the whole thing. And I did put for you here. If I take the whole thing here, now I'll tell you that's the whole thing. You measure the object first, the mass of it. Then you give the reading, the initial reading, whatever the reading is. You then insert your tilt 45 degrees. You insert your, as this here showing, show here. See here? First the mass. First you have to get the mass here. That's the first step. By direct weighing, if you have the cylinder, you can weigh it direct. If you have a shots, then you have to use weighing boat, tearing the weighing boat mass, and then just you weigh direct the mass of those aluminum shot. So then you come up with fill whatever number you like. The main thing they can sink the level of H2O has to be higher. So it's supposed to this amount as here mentioning this amount. Then you insert your object, aluminum, all the shot will come up to this. And the reading here, look at this, the reading here, from here to here. This is the volume of this object, correct? And here, this is another one. Let's show you here. This is the same thing here. This is the volume here. This is the beginning, this initial, this final, and this is the displacement here. Let me just erase this one here again and show you. So guys, here it is. This is the initial one. This is the final one. And the difference between those two here, the difference between those reading here will give you, this is the volume of this this shots, whatever irregular object. Correct? Now, let's do the sand. The sand is a little bit more trickier than those two. Why is the sand is trickier? Because the aluminum shot, although you have seen them, although they are irregular, but they are metals. They are made of metals, and therefore the shots, they have very packed, dense interaction with each other. So there is no air bubbles between those particles of these shots. However, sand has a problem. Sand is very porous. When I say porous, means porous, it does have a lot of air trapped in between. So we'll do two ways of determination of the sand. We'll determine the apparent one, the not true one, not really true one, because we did not correct for the air bubbles inside. And then one we'll do with correction of the air, correct? Correct for this air bubble. We will correct the way we measure the exact volume using the pirettes. I'll show you how to use the pirettes. And we'll measure this one by stirring. When you stir the sand with the tabor molecules will come and push the air out of those porous holes or spaces inside the sand. So let's determine the sand now together here. Let me name this one here again. Now we'll use the direct method. So direct method, you'll take, here it is, guys. Graduate cylinder that's 25 is this one here is 10. This one here is 100. The 25 maybe in the back. but it does not matter. It has to be with 100. You can't even do it. So weigh and record the mass of a clean graduate cylinder. So first, you'll take the graduate cylinder as is. Correct? This is 100. It can be used. So you go and weigh it empty. Correct? Then you will add the mark 10 sand. So you add up to the mark 10 sand, correct? Are you following here? We'll add how much? We'll add sand. Sand is here. Again, after you are done with the sand, do not throw it away. Not throw it away. It will be wet, but we can let it air dry, then reuse it. So do not throw it away, please. I'll put some tissue so we can collect those dry objects back. So if you look at this, now I have what? I have 10 mLs, correct? 10 mLs. But I know the weight because I weighed this one empty. I put it up to the 10. Go and reweigh it. The difference in masses, empty and filled with the sand, will give me the mass of the sand. And then I will divide it. If I divide it by 10, this is not really true. Did I correct for the air? No, I did not correct for the air. So I put it as is. So this is direct method, but I'm measuring the non-true density. Why? Because I did not correct for the air bubbles there. I just weigh this one empty, fill it up to the 10, exactly 10. Right? Reweigh it again. The difference that will be the mass, and then I use the volume as 10. That's not really true because I did not correct for the air. So that will give me what? That will give me the apparent one, non-true one. So if I have to do the true one, I have to add a liquid that will be able, tabor, for example, will be able to what? To drive the air bubbles out by mixing and adding this tabor inside this graduate cylinder will take this out. So anything about the direct method? Anything about the direct method? So the direct method is straightforward, correct? No H2O added. Direct method, we will not add. We just add this one empty, and then we'll add up to the 10 marker of the sand. Reweigh, that's the mass. And we divide it by 10. That's not really, that's actually not really 10 because you have a lot of air bubbles. So then you will do it the displacement method, which is much more accurate. That's the true density. So the first one, the direct method, is called the apparent, non-true density. Now, with this one here, I have to use the purette. Somebody has seen how to use the purettes? The purette, I have the purette here for you. I'll show you when we are done with everything, how to use the purette. Somebody had to use the purette in the high school lab or something? Somebody? Okay, so you know what the purette is. The purette is one of the very precise glass tool, and therefore it's reflecting its price. If you have a beaker, the beaker, if you take it in bulk, will cost you a couple cents. Beaker are not, they are crude, they are not calibrated very, very well. So beaker like this is a couple cents. If you take a bulk like 1,000 beaker, come for like a couple cents. But you cannot do with the purette. A purette by itself, depending what reading it might read, it can take up to $60, $70. So a couple cents to $70, you can know why is this very expensive. This is very cheap. This is very cheap because it's not. It tell you 10 mLs, 20 mLs. It's not really 20 mLs. Just crude, maybe 8 mLs. Right? Just a crude. It's not calibrated. Those are values not calibrated. Same thing with the flask, Almar flask, not calibrated. This one's expensive. This one's calibrated. Anytime you have a very good calibration, which will deliver for you, glassware which will deliver for you very good precise values, the value will reflect in the precision, which is very, very expensive. Very, very expensive. So please do not break any Purex. breaks my heart because it's very expensive to replace. A nickel is okay. Those are a couple cents, no problem. So we buy them. We buy them from a couple, like about 2,000, 5,000. So they are not very expensive. So now I did this is direct. Direct method. We say this is not true density. Empty, fill it with 10 mils. Sand, reweigh. That's the difference in mass divided by the 10. This is the apparent non-true density. Whatever the mass of the sand divided by 10. Now the much more precise one is to add exact amount of liquid. That liquid is able to drive the air bubbles away. And we will stir too. So here it is, the displacement method. Let me go and so here it is. So what we'll do here, you will add 10 mils of H2O to the bread. So you will do the same thing you did before. So you weigh this one empty. You might have not did this because you know the mass of it in the beginning. Empty, and then you fill it up to 10 mils, correct? Now you will add to it. So you read the reading. That's you take the reading. You know this. You added 10 mils, but that's not the true volume. So you will go to burette, and you will add. You will record the burette's initial reading. So suppose you start from 0. So record 0. Then you let it run to 10. Okay. So and then you put that. You put this one underneath the sand. So from 0 to 10, you stop. Everybody's following me here? So the difference in the volume you have read is the true volume is coming not from reading this, coming from what? From the burettes. If you look guys here. Let me get out of this. So you can follow the procedure here. Look, guys. This is the direct method, correct? So if I look at this one here, that's the sand. So you can follow the here it is, guys. Look at this. We fill this one empty. I mean, we weigh this one empty, correct? And then we fill it with sand, 10 mils. The difference of the masses is the mass of the sand. You divide by 10. This is all about direct method. So you assume this 10, right? And this is called apparent density, not true density, because the volume is not. Now, when you use the displacement, you use the burette. You start with 0, for example, mel, and you can get 2 digits after the decimal, 0, 0. So here it is, 0, 0 mel. And then you put it whatever is maybe 9.9 mel. So the difference between them will be coming here. That's your volume, correct? So now you have exact amount from the burettes. Are you following? Now you will start mixing. Now when you start mixing here, you will see that the volume from the burette. We will see that's the sand and the H2O when you after the mixing might be not 9.00, correct? Might be not 00. Are you following me here? Will be a little bit off. So then you read whenever after mixing, you read the second the real value. It's here. You divide it by whatever you have entered from the burette. That will give you the volume of the sand. The mass of the sand you already determined by empty, way of this empty. You added them at the sand, 10 mils, the sand, you weigh again. Difference will be the mass of the sand. You added exact from the burette, 10 mils, correct? So you know from the burette you added 9.90, and here you read 10. You mix, and then you see after mixing, the sand will displace the H2O, and then the tabor will get out of all the air bubbles, and your reading will be higher a little bit than maybe 10, 10.5, or 11, a couple few milliliters more because the sand is displacing H2O, and then you take the reading. The final reading minus the burette reading will give you the volume of the sand and the mass you have it. So you can determine the density is this one here, and this one is coming from this, correct, and from this. This after mixing here. Oops, this one here after mixing. Here, this after mixing, by the way, here. Mixing after mixing. Okay, guys. Then we'll have salt. Here it is. Density of the salt. Now, here is the same thing. So you take a graduate cylinder, which is 25. I have 10 and 100. So suppose here, so let's look back here. Let me get out of this. The same thing, just to show you here. With the sand, you will use two liquids, one with H2O, one with alcohol. So you will take, density using H2O. You will take this one here, empty, correct? Empty. By the way, if you take one graduate cylinder, stay with it. So you know its mass. You don't have to wait every time empty. So you know how much is weighing when it is empty. Take it here. Here is your salt. This is your salt here, correct? The whole idea, I need to know the mass of the salt. So you will fill the graduate cylinder, the same thing you did with the sand, up to 10 mils, right? And you go a reweigh again. The graduate cylinder filled with the salt, filled minus the graduate cylinder empty. You don't have to wait empty. You wait once. You keep yourself. Do not switch graduate cylinder. If you took one, stay with it until the end of the lab. If you change graduate cylinder, that will lead to huge error. Huge error. So that's among the big errors you can if you switch glassware. So stay with it. So I know the mass of the salt. I need to get what? I need to get the volume. I do the same thing with the burette. I add to the salt 10 mils from the burette, initial and final. And then when we add initial and final, I put this whole thing there. And then I mix. I know how much I add from the burette. I know the displacement of the salt of H2O, how much is it? Correct? This one I will not mix. If you start mixing, then some of the salt will what? Disappear in H2O. So keep it as is. Don't mix it. The salt is physically react with the tabor dissolve. Keep it as is and see the difference, the displacement, final minus initial here. The initial started from the burette, correct? And here when you add it, the salt, when you add the tabor, so it will go up. The difference will be the volume, and you divide by the mass of this salt here. You determine the sodium chloride density. Now, if I can use the website and say, okay, I suspect that the aluminum is my unknown solid. So then I will say, okay, aluminum density is 2.70 gram per centimeter cube. Right? I am looking at the sand. Depending on the sand is silicon dioxide. So sand density. Well, the sand density will depend on what type of sand and from what places you have taken it. So from what ocean, whatever is that really is. But generally, sand is, you can see, is heavier. is you can transform this one here in gram per centimeter. So is so let me just take it. It's 1.71 gram per centimeter. It's less than aluminum, It's 1.7. So it's 1.7. So the unknown, I don't know what the unknown is, but you can tell what the unknown is, and then you look at the sum of the densities. So the density of aluminum and density of sand and sodium chloride. How about sodium chloride? Sodium chloride density. Why I'm showing this to you, because this one here, you know how you did. It comes to discussion, then you can, okay, according to the literature, sodium chloride density is 2.16 gram per centimeter cube. However, I got this. So maybe the source of error, I'm off from this value because of this. You did not do very well, or you did not read the burette very well. You did not read the grad cylinder very well. So that reading will always, or you did not weigh, or did not read the balance very well. So all this weighing and volume reading, it's affecting your densities, correct? With the assumption that all the densities are 25 degrees, 1 atmospheric pressure. So let's start, and I'm telling you that that's experiment number 2. I have only 9 students. We have 20 students in the class. So we have 9 students, 5 already submitted. I grade them, and 4 is still at large. I'll grade them tonight. And tonight I'll put for you the quiz number 1, which will cover density and significant figures. So it will cover multiple choices, lockdown browser. You can use anything you want, open book. Okay, but it's time limited. If you don't know how to do them, the time will be running out, and then you'll be just looking from one page to one page, and the time will be out. Are you following me here? So you have to study the examples, and after the if you look at the guys, if you look at the listen here, if you look at the whole thing here, this is the whole thing. This is the data here, correct? And when you have done the data, then you will do discussion. I'll show you, and then you will do the post-lab questions. You have to do them after the conclusion. Now, those post-lab questions may be similar to those will come in the quiz and maybe in the midterm. So I'm not giving you questions you have never seen. I don't put this. No, that's not fair for students. I have even I have a problem with the ACS exam. Sometimes mention things not even discussed. So look at this, answer those. If you have problem how to solve them, come and see me. But you have to study them for the quiz. So you have to study them for the quiz. Now, let's start. Every group 2 or 3, maximum 3, minimum 2. And you can choose any place you want. And you can choose or select any partners, any classmates you want to work with. The main thing you have to work. And I have to make sure that you use goggles over there, clean them and rinse them. And I'm going through, I see who had brought sandals today. Somebody had brought sandals? No sandals, no food, please. No food and no sandals for your own sake. Okay, guys, let's start doing the lab. Thank you very much, and I'll stop recording.